Good evening, ladies and gentlemen, students. Arthur Johnson speaking, and we will be having our meeting tonight to talk about nucleosynthesis. I'll come to that in just a minute. I wanted to do just a little bit of housekeeping with you here and bring you up to date on the comet, which we talked about some weeks ago. This is a picture from the Hubble Space Telescope, and it shows that the comet is continuing to disintegrate into smaller fragments. So it's not unexpected, but we're not going to get the brilliant show that we had once hoped we might. But oh well. In other news, the one time we managed to get a real stargaze going, and some of you will remember what a cold night that was, I talked about Betelgeuse, the brightest star in Orion, which had noticeably dimmed from January to December of last year, but the news on it is it's now brightening back up again, so oh well. Again, it may go supernova someday, and shortly we'll talk about what that might mean, but it is brightening back up and more or less looking like its old normal self. Well, this is a mouthful, nucleosynthesis. It is basically how do you make a new chemical element or a new kind of atom that you didn't have before. That's what I'm going to try to talk about tonight. And this is my first time giving this lecture, so it may not be as polished as I would like it to be, but hey, we start somewhere. Another way of phrasing the question or the title is, how did all those chemical elements come into being in the first place? Through much of Western history, it was assumed that the universe had always been as it was, or that it was created by supernatural forces, and that all of the chemicals that were to be found had always been around. Nobody really talked about the genesis of new kinds of atoms, not even a bit. But in the last century, that has definitely become a field for scientific endeavor. Now, chemistry is an honorable science, at least I think it is, but it is one that took a while to get into its maturity. And if you go back to very early times, about the extent of chemistry was that the ancient Romans knew there were 7 different kinds of metals: gold, silver, zinc, a couple of others, copper. But the science of chemistry really wasn't formed yet. Around 300 BCE, for a few centuries, there were alchemists whose work was to try to transmute cheap metals into gold, and good luck with that. Didn't work too well. But the number of different chemical elements known was not great. Over the centuries, more and more were discovered. It was not until the time of the American Revolution, roughly, that hydrogen, oxygen, nitrogen were discovered to exist. They were isolated by chemists. And so the progress came on. By 1940, there were something like 92 known chemical elements out through element 92 on the periodic table. But atoms were somewhat of an intellectual construct. They were, well, Democritus had imagined way back in something like 300 BCE that all matter could be broken down into small chunks, an atom, and below the size of an atom you could not go. But nobody really knew if atoms existed. It was a useful intellectual construct, but it was really not until about the turn of the 20th century that Rutherford and other scientists cracked that mystery. And indeed, Rutherford found that the proton, that's not right. He discovered the atomic nucleus in 1911. Subsequently, the nucleus was revealed that it could have 2 different parts: the positively or the charged proton and the neutron, which wasn't found until 1932, and the negatively charged electron, which orbits the nucleus of an atom, had been discovered back in 1897. Any of you who had high school chemistry classes or might be taking one now at TMCC will recognize the familiar periodic table of the elements. Now we're up to 113 of them or something like that. Many of them are human-made and do not exist in nature and will not remain for very long. But That's off the point a little bit. Astronomers used the spectroscope and the telescope to find out that most all the chemicals known on Earth also existed in the sun and in many of the stars. It's interesting to note that the second most abundant element, helium, was not even known to exist on the Earth. It was first discovered in the spectrum of the sun in 1868, and it was almost 30 years later before it was isolated and found to exist on Earth. Well, classical chemistry, the kind that prevailed for many, many hundreds of years, held that matter cannot be created, matter cannot be destroyed. Chemical reactions can rearrange atoms and radicals into other things, other molecules. The old illustration used to be used about a house. If your house is built of wood and stone and so forth, you have a big house fire, the house is gone, but all the atoms that were originally in the house still exist. They simply went somewhere else. But as astronomers looked at the stars and the sun, it was not exactly obvious what gave them their energy. If the sun were made of coal or some similar thing, scientists calculated that it would be all burnt up in just a few thousands of years, and yet we knew that the sun had been around for a really long time, and it led scientists to ask the question, well, what else could be going on here? So we talked about the discovery that the atom had component parts, and became possible to change one chemical element into another, transmutation. Originally thought that can't possibly be, but Rutherford did it in 1919. It was done during World War II with the horrific atomic weapons. And at the heart of why this can happen is Einstein's famous equation, E equals mc squared. It is to say there's an equivalency between mass and energy. You can turn mass into energy. So only by around 1939 was it clearly established that the sun is in fact a nuclear furnace and is actively transforming hydrogen into helium. So the stars are nuclear furnaces. They are capable of transforming one element into another. And the key to how that happens is the pressure. A huge, huge cloud of gas forms, condenses into a star, and we'll see how that plays out in just a minute. But we really need to go back to the theory of the Big Bang, and that is a TV show, but it's also one of the theories about how the universe came to be. That term was actually first coined about 1949 by an astronomer named Fred Hoyle. And by the way, he didn't believe it himself, but he used it to describe the idea that everything in the universe was all once in one big place, in one small place rather, and everything exploded, blasting things outward and outward and outward, and the universe got bigger and bigger and bigger. Around 400,000 years after the Big Bang, the universe had cooled enough for the first atoms to form. Prior to that, it was so hot that there were only atomic fragments. But by 400,000 years on, we're starting to see atomic hydrogen, atomic helium. And these gases formed, condensed into the very first stars. In these first stars, hydrogen was compressed so greatly it fused into helium, releasing photons, photons of energy. If your star was a small one like the sun, it would fuse its hydrogen into helium. Then helium would fuse into carbon, carbon into neon, and so forth, down the atomic chart until you got to iron. And after iron, atoms would not fuse any longer to produce a liberating of energy. And so for a star like our own sun, when it's out of hydrogen fuel in about another 4.5 billion years, it will simply get smaller and smaller and cooler and will wind up as a white dwarf star. Not very interesting. If a star starts out its life with more than about 2.2 solar masses, if it's a bigger star, then the pressures will be so great when the iron core has formed that the star will collapse violently upon itself, producing a supernova explosion. And for a time, that star will shine brighter than all the other stars in the galaxy combined. What happens to the core of a supernova gets kind of interesting here. When the supernova explosion occurs, most of the mass of the star gets blasted out into interstellar space to blend with and merge with other clouds of gas, maybe other hydrogen and helium atoms, and a second generation of stars then may form, which incorporates the iron and other somewhat heavy elements that were formed in the first generation stars. However, there's been a problem because we know that gold, platinum, iridium, and other heavy elements exist, and the theory simply didn't explain how enough of those chemicals could be generated in a supernova explosion to account for what we see. The theory had not caught up with the observation. But very, very recently, literally within the last 3 years, we've had some really amazing breakthroughs. In August of 2017, the same month that we saw the solar eclipse, gravitational waves were detected, and we'll talk about what those are some other time, but they are predicted by Einstein's general theory, but nobody had ever seen them until pretty recently. But a detection was made of gravitational ripples in space-time caused by the collision of two neutron stars, each of them having the size of a small city, but having the mass of the Earth. And from the three gravitational wave detectors, it was possible to triangulate so as to know where to aim telescopes to see if they would detect this tremendous collision of the neutron star bodies. And sure enough, it was spotted. So now we've seen neutron stars collide, and the theory tells us that when a neutron star collides with another neutron star or with a black hole, it can generate abundant quantities of all those heavier elements. And as one scientist put it, science had literally struck gold, because heretofore we really couldn't comfortably account for the science of how there could be that much gold, platinum, and other heavy elements. And now this neutron star collision did render a successful account. And my last slide right now is the other object that was just newly discovered literally last year. You may remember the publicity that came out around the detection, the actual imaging of a black hole, which was seen in the direction of the constellation Hydra. Well, I'm going to stop and hope that we have lots of questions here. And so with that, this is Art Johnson signing off the video, and we'll come back to our live discussion.